This lecture concerns the average value of a function, the mean value theorem for integrals, and the second fundamental theorem of calculus. Now, to find the average value for a continuous function, say the average height of this blue function here, it's not a matter of simply taking the lowest number and the highest y value, lowest and highest y values, and taking the average of those two, adding up and dividing by 2. You have to understand that we have much more of the function down lower than we do up higher. That would be like taking the numbers 2, 2, 2, 2, 2, and 8 and finding the average of all of them simply by using 1, 2, and an 8. You have to do a weighted average, and for a continuous function, the way that's done is in this manner. Rather than with Riemann sums finding a lot of rectangles to approximate an area, we assume we can get the area, and then we find the average value by finding the height of that rectangle, which is the same as the area under the curve. So the area under the curve is these turquoise lines. We find that our average value will be the height of this one single rectangle in purple, which is the same as the area of the area under the curve. And so your average value is that height. And to find the solution to the mean value theorem for integrals, those are the x values between a and b. So here and over here and over here, that would give you that average value. So if you're finding the solution to the mean value theorem for integrals, as we'll see, first you need to find the average value, and then you have to go back and find the x values that give you that average value, since average value is a y value. And so our average value, again, is the height of that one rectangle, which gives us the same area as the area under the curve. So this is another way of looking at it here. It's a weighted average over a continuous function. What we have in this figure is this curve, f. I have a and b, that's my interval, and my area is outlined in yellow, and that's given by this integral from a to b of f of x dx. So this we can now do using the first fundamental theorem of calculus. And the area of this rectangle in blue, which I want to be equal to the area in yellow, is simply length times width. Now the length is the length of my interval, b minus a, and the width here, the height that is f of c, which is going to be my average value. So I've got this equation setting the area under the curve equal to the area of the rectangle, and I want to find f of c, so I simply divide both sides by b minus a, and I get my formula for average value, which is right here. Your average value, which is called f of c here, is 1 over b minus a, integral from a to b of f of x dx. Looks just like finding a definite integral, but you have to divide by b minus a to divide off the base of your rectangle to get your height. And then once you have f of c, you can go back and actually find any values of c within your interval, which will be solutions to the mean value theorem for integrals. So a few examples. Here I've got the function f of x equals x squared plus 1 from 1 to 3. And to get the average value, you do 1 over b minus a times the integral from a to b of f of x dx. And so this becomes a half. I integrate x squared plus 1, going from 1 to 3. So I've got the half, plug in 3, minus, plug in 1, and then we simplify it, and we get all the way down to 5 1/3. So that's the average value. So if you were to plug in 1, you'd get 1 squared plus 1 is 2. You plug in 3, 3 squared plus 1 is 10. So average of 2 and 10 is 6. We're at 5 1/3, which does make some sense because our function is not straight, it's curving. Okay, so if we just look at our figure right here, what we see is here's our parabola, and we draw a rectangle of height about 5 1/3, and the idea then is that the underestimated blue and the overestimated red cancel each other out, and that seems about right. Now if we want to actually find solution to the mean value theorem for integrals, which according to this would line up right about there, it's not halfway between our endpoints of our interval 1 and 3, you've got to take 5 1/3 and set it equal to your function, because you've got a y value, but now you need an x value, so subtract 1 and take a square root. You don't want plus or minus 2.08, you only want the positive one because you have to be within your interval from 1 to 3, and so that's your solution to your mean value theorem for integrals. Okay, now we've got the function 4 minus x squared from negative 2 to 2. Here's your average value formula. So we'll have 1 over 2 minus negative 2 going from negative 2 to 2 of 4 minus x squared. So then I get 1/4 negative 2 to 2, 4 minus x squared. Before I integrated, I realizing that 4 minus x squared is an even function, I just go from 0 to 2 and double it. So the fourth becomes a half. Not necessary, but it makes the computation easier later, having a 0. And then I integrate 4 minus x squared. I anti-differentiate that. Plug in the 2 here. And then when you plug in 0, of course there's zeros. And so that is your average value is 8/3. Now to get the solution to the mean value theorem for integrals, plug 8/3 back into your y value to get your x value. So 8/3 equals 4 minus x squared. So therefore x is plus or minus 2 over rad 3, both of which are within our interval. Okay, 2 secant squared x from negative pi over 4 to pi over 4. So 1 over b minus a, integral from a to b of f of x dx. So this becomes 2 over pi. I brought the 2 out front. Once again, secant squared is an even function, so I go from 0 to pi over 4 instead of negative pi over 4 to pi over 4, and then this 4 over pi became an 8 over pi. Not necessary, but helpful. Integral of secant squared is tan x. Plug in pi over 4 to get 1. Tan pi over 4 is 1, tan is 0, 0. So my average value is 8 over pi. To go ahead back and get my mean value theorem for integrals solution, 8 over pi is set equal to your function, and you've got to figure out what that's going to be. So roughly speaking, it's the inverse cosine of plus rad pi over 4 and negative rad pi over 4, those two. And lastly, before we go into second fundamental theorem of calculus, average value of cosine from negative pi over 3 to pi over 3. And so 1 over b minus a, 0 to, or a to b. And again, it's an even function. I happen to pick 3 even functions in a row. You can't always do that, of course. So you anti-differentiate and plug in your limits, and you get an average value of 3 rad 3 over 2 pi. And set that equal to your function in order to get the mean value theorem solution for integrals, and you get those two, 0.597, negative 0.597. And so here's what cosine looks like within those limits. Here's your average value up here, and 0.5 is here, and 0.6 is right there, and you can see I'm right around where 0.6 is and negative 0.6. So this is about what I would expect. Also, these areas seem to cancel, so graphically speaking, it looks right. Okay, second fundamental theorem of calculus is used to take derivatives of integrals. So here we have a rather complicated looking formula which is really quite easy to apply. So we have a derivative of an integral where the limits of the integral are functions of this, this outer variable with which we're taking a derivative with respect to. So what you do basically is you plug in the upper limit, f of b of x, times the derivative of the upper limit times b prime, minus, plug in the lower limit, f of a of x, times the derivative of the lower limit, a prime. So here it is, plug in the upper limit, multiply by the derivative of the upper limit. It's like a chain rule effect. Plug in lower limit, multiply by the derivative of the lower limit, subtract the 2, and remember derivative of a constant is equal to 0. So a few examples. Don't try to integrate this and then differentiate and plug in limits, differentiate it. Just use the second fundamental theorem of calculus. You could integrate this one, differentiate it, but it's so much more work. So you plug in sine and get sine squared, times the derivative of sine, which is cosine, minus, plug in the lower limit, so x squared squared, times the derivative of x squared, which is 2x. This comes down here, and this becomes 2x to the 5th. Okay, this is one we'll learn how to integrate later using natural log, but again, don't bother. Just use the second fundamental theorem of calculus. So plug in the upper limit, 1 over tan, times the derivative of that, secant squared, minus, plug in the lower limit, 1 over x to the 4th, times the derivative of x to the 4th, 4x cubed. All this trig you can simplify to 1 over sine times cosine, and this can cancel the 4 over x. Okay, over here, plug in the upper limit. So e to the negative sine x plus 2 times the derivative of x plus 2, which is 1, minus, plug in the lower limit, times the derivative of pi. Pi is a constant, so the derivative is 0. All this just becomes e to the negative sine of x plus 2.